Okay, very good. So it's a pleasure to introduce Ziqi from NORDITA, and he will speak about a BPS road to holography and matrix theory.
Thanks a lot, Charlotte. So, sorry. Anyway, this is the. Okay, that's working. So I would like to start with thanking all the organizers for bringing all of us together and, of course, for inviting me, for which I'm very much honored. So apparently I'm going to discuss a BPS road, which might sound a bit mundane, but I promise that there are some surprises on the road. Okay, I'm already spoiling the surprise. But anyway, so this talk will be based on my recent works through the past 2 years in collaboration with a by now quite sizable community. So I'll be mostly focusing on this set of papers and work in progress, but I also borrow important key insights from my other recent works in collaboration with a group of people, and many of them actually sitting in the audience. I have to apologize, I cannot really go through all the names here, but I do like to refer to Truls Hammerk's talk tomorrow on narrativistic string theory, which really provides a complementary perspective of what I'm going to discuss today. No, sorry. Apparently, I don't know how to use this. Somehow it jumped all the way down. Okay, now I'm learning. But anyway, I guess I've spoiled the whole talk already. But anyway, so wait, what is happening? I didn't do anything. It happened again. It just likes me to jump all the way to matrix theory. Maybe I should point to somewhere. Okay, hopefully now it's working. So I start with the take-home message of the whole talk. Maybe it's because when I press this button. Okay, avoid that. Which is the following. There is, at least I think, quite interesting and novel no-Lorentzian perspective that was somehow missed out on the ADS-CFT correspondence. And we were actually led to discover this by following this BPS road. And this might already sound confusing to you because you might say that isn't ADS-CFT one of the most relativistic theories that we can think of? So what is no-Lorentzian about it? Let's take a simple example. Well, it's not simple, the classic example of ADS5 CFT4. Then I have this bulk geometry ADS5 cross S5. And now if you go to this asymptotic infinity regime, you'll see various singular behaviors in 10 dimensions. So normally we're focusing on 4D, where we see these encores for supermills, that is due to gravity on this ADS bulk. But when we start thinking about this 10-dimensional geometry, that becomes singular. And that is where these no-Lorentzian geometric insights will be helpful. And this perspective is especially important exactly because it makes this BPS nature of both holography and matrix theory very manifest. And using this perspective, we can form a framework to classify holography in string theory, not only for the ones related to an ADS bulk geometry, but also for the ones related to possibly the Sitter, flat space, and even no-Lorentzian bulk geometries. And moreover, this no-Lorentzian perspective provides us a chance to revisit this finite n version of BFS conjecture for matrix theory, which I think is very much complementary to the recent revival of matrix theory from both communities of amplitudes and conformal bootstrap. And also there was this very nice talk by Jackson Fliss yesterday from the perspective of entanglement entropy that I have learned about. Okay, so first the holography part. Now it's working, so that's good. No? Okay, I said that too early. Maybe the battery is down, maybe that's why. But anyway, so let me start with illustrating this non-Lorentzian perspective by starting with the classic example of ADS5 CFT4. And here I'm just giving you the full bulk geometry, that is this 10-dimensional ADS5 cross S5. And I have introduced this parameter omega, which is proportional to the square of the radial direction r. So now if you go to this asymptotic infinity regime, we're essentially sending omega to infinity. And now if you look at this line element, you'll see that it becomes singular. So that is where this 10-dimensional metric description becomes invalid. And this is exactly where you see this non-Lorentzian geometric description becomes useful. So we actually end up with a 10-dimensional Galilei-like geometry where we have a Galilean type of boost that maps the transverse sector to the longitudinal sector. There's yet another interesting regime, which I won't have time to talk about. That's when you send this omega to 0. So if you think about the thermal case, you're basically zooming on these horizons associated with the black brane. So probably not surprisingly, we'll see this effective geometry that is Carroll-like. But let's return to this asymptotic infinity regime. What I have said might not be very satisfactory to you because all you can see at the moment is that there's some 10-dimensional geometry that becomes singular. So you might ask the question, if we say that this is Galilei-like, well, is this manifest the Galilei-like boost symmetry? In order to understand that, let's look at some, sorry, it's just slow. Maybe I'm standing too far away. Oh, no, it's... No. Maybe I can just use the computer. Is that... Okay, I'll do that and you can do your job. So let's try to understand this by looking at something that is more physical. So in this ADS5 CFT4 case, it's natural that we think about a probe D3 brane. So here I'm just giving you the volume, thank you, action. Okay, now it's perfect, thank you. Which is right here. So this is the volume action describing D3 brane, a probe D3 brane on this ADS5 cross S5 background. And you can see that it's reparameterized in terms of this parameter omega. So now if you send omega to infinity, that means we're going to this asymptotic infinity regime here. It's really a reparameterization of the famous Molosina limit. But if you really zoom in, you'll see what is happening is that the effective mass associated with the D3 brane is blown up. However, this divergence is exactly canceled by a fine-tuned D3 brane charge. And that's, of course, because of the underlying supersymmetry. So after all, what we're really doing is by taking a BPS decoupling limit, zooming on a background D3 brane. And the leftover modes are exactly these new BPS states, which are also well captured by this limiting procedure. So here I'm just talking about a single D3 brane, but you can also consider a stack of coinciding D3 branes, in which case we're not abelianizing this free action to be exactly n equals 4 super mils, that is corresponding to gravity on this background ADS5 times S5 geometry. But for simplicity, let's just focus on this single brane case. And there you can check explicitly that this is really invariant under this Galilei-like boost transformation up to some boundary term. So what is happening here is that by taking this BPS decoupling limit, we have blown up a background D3 brane, which leads to this spontaneous symmetry breaking of the space-time symmetry. And we're left with this geometry, where I have a 4-dimensional sector aligned with the background D3 brane, which kind of replaces the absolute time direction in Newtonian physics. Moreover, we have this 6-dimensional transverse sector that is mapped to this 4-dimensional longitudinal sector with this Galilei-like boost symmetry. Okay, So in a word, this n equals 4 superamines that are super familiar with actually sees a 10-dimensional Galilei-like geometry. Moreover, if you compactify, maybe the problem is really about me. Okay, I'm sorry. So if you compactify these D3 branes over some internal 3 manifold, and for simplicity, let's take it to be a 3 twirls. Then I have these wrapped D3 branes interacting with each other. And now the gravitational force is really Newton-like instantaneous force. Moreover, you can tedialize on these 3 twirls. So that's the standard relation that maps n equals 4 superamines to be n equals 16 superamines in 0 plus 1 dimension, which is precisely BFSS matrix quantum mechanics. And this T-duality also maps the D3 branes, the wrapped ones, to D0 particles, whose dynamics is described by BFSS matrix theory. So what we end up with is actually the picture of a bunch of relativistic D0 particles interacting with each other via these Newton-like forces. But holographically, it becomes a bit more complex. So the original ADS5 geometry is now mapped to this conformally ADS2 geometry together with an 8 sphere. But this geometry is only good for a region. And that's because there's a key difference here. The dilaton has developed some profile, so it's a function of this radial direction. And now if you go to the center of the bulk, you'll see that the string coupling really grows, and you're actually entering the M3 region. But this is nothing but this modern holographic perspective of the old BFSS conjecture, which says that the large N limit of BFSS matrix quantum mechanics describes you the full M3 in an asymptotically flat spacetime. This is always very difficult. Okay, it's still working. But there's actually also some interesting property of this infinite omega limit. Actually, after you take this essentially BPS decoupling limit, you'll see an emergent dilatation symmetry, which means even though we have taken this omega to be dependent on the radial direction, but actually it doesn't matter what kind of detailed form this omega takes. For simplicity, you can even take this omega to be a constant. But that leads us to a change of philosophy. So I have been saying that this no-Lorentzian feature arises by going to this asymptotic infinity regime of the ADS bulk. But there's more to it. And now you can actually think about applying this BPS decoupling limit to a full-fledged string theory. And in this case, it will be type 2A superstring theory. So what we do is the following. We take type 2A superstring theory and reparameterize all the background fields in this particular way with a constant omega. So if you send omega to infinity, you'll still get the same theory. So here I've been sticking to a flat spacetime, but actually you can also make it curved, which I'm going to do near the end of the talk when it becomes actually necessary. And now if you take this BPS decoupling limit by sending omega to infinity in the full type 2A, you should be led to this self-contained corner that is also a full-fledged string theory. And I have to give a name to it, so calling it matrix zero brane theory for obvious reason, and M0T for short. And please do remember this acronym because I'm actually going to use it for the rest of the talk. So what it describes is essentially, the dynamics is captured by these light excitations that are these zero branes, whose dynamics is described by BFSS matrix quantum mechanics. But because we say this is a full-fledged string theory, we should also consider other extended objects, for example, the fundamental string. Except that, as we'll see very soon, this fundamental string won't be fundamental anymore. It doesn't have vibrations, so it's highly no-perturbative. And in that sense, this M0T is really a no-perturbative string theory. Okay? And moreover, this omega going to infinity limit that leads to M0T can be further interpreted as an infinite speed of light limit by sending this C to infinity. To understand that, let's again focus on a probe D0 brane in this theory. So we start with the D0 brane in type 2A superstring theory, which is nothing but this relativistic particle coupled to some U1 potential. So I have recovered all the dependence on the speed of light c. Moreover, I have fine-tuned the charge so that it's canceling the divergent D0 brane mass mc squared when c is taken to infinity. And after a trivial rewriting, you can see that the reparameterizations of the dilaton, line element, and Raman 1 form are matched on to these reparameterizations of the background fields that we introduced earlier, as long as you identify omega with C. So now if you take this BPS decoupling limit by sending C or omega to infinity, you'll get these new BPS states described by this relativistic particle action. And again, if you instead consider a stack of D0 branes, you'll now abelianize this theory to be BFSS matrix quantum mechanics. Okay, so this procedure sounds like the usual relativistic limit of relativistic particle that gives you Newtonian physics, but there's a key difference. So there we always have a rest mass mc squared that we just set aside. But here it's very important that this rest mass is cancelled by the critical charge, so that we have underlying supersymmetry protecting these BPS conditions. Okay. Now it's the nightmare again. maybe I just have to be close by. But as I've said, this M0T is supposed to be a full-fledged string theory. So let's also look at some other modes which are not the D0 branes. For example, this fundamental string. And we kind of already know how to get this M0T fundamental string from the usual Polyakov action. And here I'm just going to focus on this bosonic sector. So what we do is, again, that we recover all the dependence on the speed of light, and then send this C to infinity. So that's the same as sending omega to infinity. But there's a key difference here. So we no longer have any critical charge that we can use to cancel the divergence from this sector. And that's why we still have divergence in the system, which leads to these constraints that are imposed by introducing this Lagrange multiplier that we call lambda. Okay? So this is exactly the reason why the string becomes node adaptive and is actually node vibrating. And you can check that the target space geometry is indeed satisfying this Galilean type of boost symmetry. And moreover, the wall sheet is also non-Lorentzian in this case. And that's because there's no trivial dependence on the speed of light on the wall sheet. Topologically, what it does is that it introduces various pinchings on the Riemann surfaces. And we're actually led to these string topologies, which are pinched, that are used in ambiguous string theory to compute string amplitudes. But this is not a coincidence at all. So in fact, if you consider this T-duality along time-like direction, which was pioneered by Chris Hall in the audience, and in this case, you apply it to this M0T fundamental string. So you can derive this new action, which is actually the same one as you can get by sending the tension of the string to 0 in usual Polyakov string theory. So this leads us to a tensionless string theory, and that's actually coming from here in Sweden. So now, if you further go to this ambitwistor string gauge, you'll recover, at least classically, this chiral sector described by ambitwistor string theory. That explains the similarity at the level of the wall sheet, and it's because T-duality doesn't really change the wall sheet structure. By the way, this is actually the same type of limit that Bo Songbori and Lawrence Eberhard already discussed in the next talks. Okay. But if you think holographically, this actually implies something I think quite interesting. So let's go back to the M0T string. In that case, we know the fundamental string doesn't really capture the light excitations. Instead, you have to focus on the D0 branes, and therefore BFSS matrix quantum mechanics. So when you think about the time-like T-duality, you should really apply it to BFSS. And that leads us to IKKT matrix theory on instantons. Holographically, you'll see that the bulk geometry should be flat space. I think friends Cecilia will be discussing something related to this tomorrow, so I won't say too much about the precise relations here. But furthermore, if you start doing these more regular space-like teleology transformations, you actually be led to this de Sitter-like bulk geometry a la Chris Ho. And now if you go to this asymptotic infinity regime, you discover 10-dimensional Carroll-like geometries. So in some sense, this time-like teleology transformation is really like a looking glass that tunnels us from ADS-FT to other type of holographic constructions. But the story doesn't stop here. So let's just ponder over what we have done. So what we have done was that we started with the bulk geometry that is relativistic, and we went to this asymptotic infinity. But you can also reverse that, and that's actually the true power of this whole program. So instead of starting with the bulk, it's actually easier to start with the BPS decoupling limits. And you can classify these BPS decoupling limits by really understanding the no-Lorentzian geometry behind them. And then there's actually a well-defined deformation that is due to the TT bar deformation that Roberto was reviewing very nicely earlier this morning. And they'll generate you this bulk geometry. In this case, they're relativistic. But also, you don't have to stop there. Not only you can apply a single BPS decoupling limit asymptotically, you can also apply a set of consecutive BPS decoupling limits. And these limits are actually well organized by what we call DLCQ, that is short for discrete Lycon quantization, that I'll discuss a bit more later. And there's actually this very prescient work from 20 plus years ago, which is unpublished, where they already understood this type of perspective, but from the BPS mass spectral. And now we're blending in this geometric interpretation, which is no Lorentzian. And in this case, now if you turn on this generalized TT bar deformation, I forgot a key sentence. So in general, holographically, this BPS decoupling limit will be mapped to a near horizon limit in the bulk that leads to this set of geometries. But in the most general setup, you don't need all BPS decoupling limits to be mapped to near horizon limits, but instead you just need a portion of them be mapped to near horizon limits, and the remaining are still the BPS decoupling limits that I have seen asymptotically, and they'll lead us to this no-Lorentzian bulk geometry. And this provides us a chance of understanding possibly no-Lorentzian holography from top down, which has been explored quite a lot recently. Okay, so this is basically what I want to say about the holographic part of the story. But before I move on to matrix theory, I think it's necessary that I say a few words about the M-theory uplift of M0T, which I hope will help you understand what is going on. So again, I'm showing this M0T limiting prescription parameterized by this constant omega. So if you send omega to infinity in type 2A superstring theory, you'll get M0T. I'm just repeating what I have said for multiple times. But for this prescription, before you take the limit, it's easy to uplift to 11 dimensions in M theory. So this is just the standard Kaluza-Klein reduction, where we compactify M theory over this space-like circle that we call Y. Oh, I already don't have any time. Oh, thank you. That's a negative one, that's why. In this case, you can, there's an interesting question that you can ask. What if we apply this infinite omega limit at the level of this 11D? That actually turns this space-like circle into a light-like circle, which means that it led to the so-called discrete Lycon quantization of M3, well, DLCQ is short for, well, and for short we call it DLCQ. And this is just a fancy way of saying that we have a light-like circle here. So now if you do this null compactification, you'll get back M0T. So normally you'll think that this like circle is quite exotic, but actually in string theory or M theory, you can utilize it so that it's mapped to a space-like circle, except that the target space geometry now becomes non-Lorentzian. And in this case, the light excitations are exactly the Kaluza-Klein modes in this light-like circle, so that they are mapped to D0 particles in M0T described by BFSS. Okay, so finally we can move on to the matrix theory side, but I guess I have to speed up here. Sorry. Okay, so let's first review a bit the original BFSS conjecture, which says the following. You start with a bound state of n D0 particles in M0T, which is described by this matrix quantum mechanical theory that is n equals 16 supermills in 0+1 dimension. From the M theory perspective, you have this supergraviton instead of the D0 brains with a discrete light-like momentum. In the large n limit, this light-like momentum becomes continuous, and that's when you see a decompactification limit. And hence the conjecture, the large n limit of BFSS should describe as the full M theory in asymptotically flat spacetime. Okay, so we can test this by thinking about this iconal scattering between bound states of D0 brains. So there has been quite a lot, very exciting new developments on understanding the non-perturbative aspects of BFSS as well as its BMN variants. But here I'm actually just going to focus on this old school perturbative calculation back in the days. So what we're computing is this iconal scattering between D0 brains, where we have one bound state of N1 D0 brains and another bound state of N2 D0 brains. We also go to this rest frame where this first bound state is at rest, and the second one is moving at the speed v. And we take the impact parameter to be very large and the potential to be very small. Okay, and then you can go through the calculation, which is done in these very nice papers and also explored in many other papers that I haven't cited here. And eventually, what you can compute is this effective potential between the bound states. And I'm only giving you the one loop result here, which I'm going to use later. Okay, and this calculation, when BFSS is perturbative, is valid when the effective coupling is small. That means finite n and small radius for this light-like circle in M3. But that's exactly when this 11-dimensional supergravity fails. However, if you do perturbative supergravity calculation, it seems that it does work for this 2-2-2 scattering. But let's try to understand why this happens again. No. Sorry about it. So now we switch to this perturbative 11D supergravity, where instead of having the D0 particles, we have the supergravitons. And if you take N1 to be much larger than N2, you'll say that, okay, this is a source particle and that's a probe particle. So I can just backreact these supergravitons to get this Eichelberg metric. And then when I consider the motion of this second supergraviton in this potential, we can compute this effective potential. So this is done in this very nice paper by Becker, Puchinsky, and Zetlin back then. But now if you look at this Eichelberg metric, it gains this deformation that depends on omega. Okay? But that means we're actually not having a DLCQ because this X minus is actually space-like. So now if you do a dimensional reduction to type 2A, you'll see that you're actually back to this conformally ADS2 geometry together with an A sphere. So in some sense, we're back to holography. And this works when the string coupling is very small, and also when you have large n, so that the effective coupling for BFSS is large. So what I'm doing here is that when you say there's a perturbative calculation in BFSS and a perturbative supergravity calculation, we're really computing things in different energy regimes. And usually you don't expect detailed dynamics to match, but because of holography, you do expect protected objects, for example, this 2-2-2 scattering, to work out. So probably it's not surprising that if you go to higher order terms, there are actually clear mismatches. Okay? But this has been known, and it seems that we should just try to improve our understanding of the large n limit of BFSS. which is actually happening right now. And there are many different efforts towards this. But to me, there's also another important question. You can also ask, what is this productive/finite n BFSS matrix theory? We know that, okay, this is 11-dimensional supergravity in DLCQ, and you compactify it along this lilac circle and shrink the circle to be very small. But this sounds very singular. So the usual take is that this is just like a very singular thing to consider. Thank you. So probably it just doesn't make sense. But now with our new insights from no-Lorentzian geometry, we can say that this is singular, that's true, but in an understandable way. It should lead us to this no-Lorentzian M0T supergravity, at least for the effective gravity description. There are also other modes. Okay, so what does that mean? So I have talked about this M0T prescription before in flat space-time, but now I have to make it curved. But that's pretty straightforward. You can just borrow this nicely developed Newton-Gacton formalism in Newtonian gravity. So you take the absolute time direction and covariantize it by introducing this temporal Wilbur field. And moreover, we can introduce this spatial Wilbur field to form a metric that is transverse. So this is not a 10-dimensional metric because it's of rank 9. And even though we don't really have a metric description anymore, but we can use this geometric data to covariantize our flat space M0T prescription to be something like this. So you can see that in this Ramon sector, we have the critical part, but also a finite piece in omega. And that's exactly acting as the Newton potential in this no-Lorentzian supergravity. So now if you plug this set of answers back into type 2a supergravity and take omega to infinity, we expect that we should be able to rid of at least some interesting dynamics from it. But this is still an ongoing project, so there's still many things that are unknown for this M0T supergravity, but I think that's also exactly what makes it exciting. It's such a new theory in some way. But before I go to the dynamics in the last slide, let me just recap a bit. So what we're observing is that if you think about a finite n, or I should say small n, BFSS, it's really a D0 particle volt line formalism for this 10-dimensional no-Lorentzian quantum gravity. And this observation is further supported by this U-dual frame to matrix string theory a la Motel, Dijkgraaf, Verlinde, and Verlinde. And this is essentially a second quantization of what we call narrativistic string theory. And again, one of the original work is also from Sweden, but it's referred to as want string theory there. And this theory arises by taking this BPS decoupling limit to zoom in on a background fundamental string. And that leads us to a perturbative string theory that is unitary and UV complete. So you can apply standard CFT techniques to compute things here. And then you can map these physical observables so you can compute here to understand this M0T. Okay? Okay, so as I have promised, we can actually rid of some interesting dynamics, at least, by following this route. So since we're talking about the Newton-like gravity theory, so you ask, what is the Poisson equation that encodes the dynamics there? And this is what you can do. You take type 2a supergravity coupled to D0 particle, so that's relativistic. And the Poisson equation arises by varying this action with respect to this omega parameter that I have introduced, which controls the BPS decoupling limit. And then you send omega to infinity. And holographically, this is like starting with the radial flow equation and push it to asymptotic infinity. Indeed, you rid of this second derivative term acting on the Newton potential. On the source side, you can see that first two leading order terms are exactly cancelled, and you're left with this sub-leading order term, which precisely reproduces you this V to the fourth dependence. And V is the relative velocity between these two bound states of D0 branes. And we should only view this as a proof of concept, because if you really want to go to higher order terms, we still need the full perturbation theory of D0 branes in M0T supergravity, and that's still to be developed. But I think it's better that I end this open question. Thank you. because I believe that this is a new arena that we can play with many old ideas, but with a new twist, and there are really a lot more to explore. Thank you very much.
Thank you very much for this nice talk. We have some questions.
Thank you. Thank you for a nice talk. Actually, I'm a bit surprised that you say that finite N BFFS matrix model is a kind of quantization for non-Lorentzian supergravity. I would say it should be just for Lorentzian gravity.
Yeah.
Because in principle, because there exist covariant versions of this matrix model in 10 dimensions and in 11 dimensions, supersymmetric and with Lorentz symmetry.
Yeah.
If you take one particle limit of BFSS, it is just, okay, you quantize particle in 11 dimensions, say,
yeah.
You should obtain 11-dimensional supergravity, and this is Lorentzian gravity.
Yes, thank you for the question. So that's exactly the normal take for BFSS, but that works in the large N limit, importantly. So the thing is that if you think about finite N, like a small N actually, then the D0 brains do not backreact into this relativistic gravity. But when they start backreacting, you'll get back.
It works even in N equal 1.
In what sense?
You have just one.
Yes.
One particle.
In what sense that you get?
It's a gauge fixed version of just much less superparticle in 11 dimensions.
Yeah, but the thing is that if you think about a single,
is normal supergravity.
Yeah, so if you think about a single D0 brain, then you really get showed it earlier. You really get a relativistic particle action. So if you think about what is probing,
in your limit.
But would you agree that this is a?
It can be considered as a gauge fixed version of relativistic particle action.
Okay, maybe we should discuss more that later. Yes, thank you.
Thanks, Ziqi. So one just outlook question maybe. Have you thought about the equivalent Carolian supergravity construction?
Yeah, so these Carol-like structures arise in various places, as we have seen very naturally in this framework. So it could be arising as this asymptotic infinity limit of the theta. And there you can already think about Carol-like gravity.
What is supergravity? So this last slide you showed with the M0T supergravity construct, did you have?
Yes, but as Chris Hall realized a long time ago, this is actually a different regime. So there's this type 2 star theory where you have instabilities. But it will be interesting to understand what kind of twists that they have if you think about this supergravity theory that is Carol-like. And there's yet another region which is more closely related to your own work. So if you go to this near horizon limit, you'll get this Carol-like structure that is not really, okay, this is not really BPS, but it has a BPS feature. But there you just don't have BPS feature at all. So there'll be another twist.
Thanks.
Thank you.